Hey everybody, Mr. Sharkey back with another exciting chemistry video. And today we're going to be looking at this last page of the types of bonds lab. Hold on, let me close this for us. A little bit of glare coming through. Um, in this lab, we were looking at electronegativity and whether or not certain compounds could conduct electricity, which means if electricity can flow through it. And here on the very last page, we get to this modeling section where we've been given three different models, and we're asked to identify which one represents ionic, covalent, and metallic bonds. So I think this is the most interesting part of this assignment, and that's why I wanted to make a video to chat with you all about it since I couldn't be at school today. So if we start off, there's a couple things I want to define before we actually start deciding which diagram represents what. And that starts off with question one. It asks us how these models represent the nucleus, how they represent the electron cloud or clouds, and then how they represent electron density. So starting off with the nucleus, I've talked with some groups about this, but to make sure we're all on the same page, what we're seeing, if I look at model A, there's one nucleus here and a second nucleus there, and that's representing two different atoms that are bonding together. So the nuclei are the black dots. So we could come in here, we could label one for reference when we get on to talk about some other stuff later. Then the next thing we're supposed to identify are the electron clouds. So the reason that it says clouds in parentheses is because in some of these bonds, atoms are actually going to share their electron cloud, whereas in one type, there is only one. There's only one atom that has its electron cloud drawn. So if we look at model A again, this ovular shape, this is the electron cloud of both atoms that have kind of morphed together. Because when they are morphing, when they're bonding together, it represents some way that their electrons are interacting with each other. In this type of bond, all of the electrons are overlapping into one shell. So both shells have become one. So we could label this as the electron shell. And then the last thing asks us about the electron density, and then tells us that electron density represents the areas where electrons are more likely to be found. So as you look at each of these images, hopefully you can pick out that there is a gradient, which means there's a section where there's a lighter color going to a darker color. And what we should see is that the darker the color is, that responds to a higher electron density. So here in the center of model A, we would expect to see a lot of electrons, or it'd be very likely for us to find electrons there. And then here at the ends where it's white, we would have a lower probability of electrons, or we could just say that there are less electrons there, or electrons are less likely to be there. And so that kind of breaks down everything that we're seeing in these models. And hopefully that gives us the terms that we need to try to identify what's happening here. The last little bit in our instructions, it tells us to explain our selections using electronegativity. So that means that as we describe things, we should be thinking about the electronegativity of atoms. If something has a high electronegativity, as we've discussed, that means there are also high attractive forces. So if I look at A, all of the electrons in A are stuck in between these two atoms. So the question you should be asking yourself is whether those atoms have a high attractive force or a low attractive force. If all of the electrons are stuck in the middle, that tells me that both atoms have a very strong hold on those electrons. So the electrons can't escape that center, and they end up getting stuck in between the two atoms. So in A, we could say that both atoms have a high electronegativity because they both have high attractive forces. And now, using the graphing lab, And using this lab, we should be able to confirm that if both atoms have a high electronegativity, that means that this is an example of a covalent bond. The word covalent, that prefix co, refers to things that are together or sharing. And then valent is referring to the valence electrons and the valence energy level. And what we see is that the electron clouds are actually overlapping. They're joining together. We also see that the electrons themselves are shared between the two atoms. And that's where we get this word covalent. The electrons are coming together. The electron clouds are coming together. So A is one extreme. We can go ahead and lock that in as a covalent bond. I think the other most obvious is not actually to go straight to B, but to look at C. If we look at C, we should notice a couple of things. Number one, we've got two atoms again. But now the atom on the left doesn't have an electron cloud. But the atom on the right has all of the electron cloud. So what that tells me is that one atom has stolen electrons from another. If this atom has no electron cloud, it's probably positively charged. If this other atom has stolen electrons, then it will become negatively charged. And now right away we can see that this is an ionic bond because we have something that is fully positive being attracted to something that is fully negative. If we want to talk about the electronegativities here, we could say that this atom on the left side has a low electronegativity. The atom on the right side has a high electronegativity. So the atom on the right was able to steal the electrons from the atom on the left. And that's why our positively charged ion has no electrons. Our negatively charged ion has all these extra electrons around it. The last thing you could look at, is notice how the gradient is getting darker the closer we get to the center of this atom. So as I get closer to the center, everything is becoming darker. That's because all the electrons are being pulled towards that negative or highly electronegative atom. So we could just process of elimination, but I think we should still talk about B. As we look at B, again, two nuclei, but this time around we've got this really big electron cloud, which gives us a little bit of a hint. And then also our gradient shows us that the electron density is highest furthest away from those nuclei. So here, these atoms are not attracting the electrons very well. They're still attracting them somewhat. The electrons aren't completely blown out, have not left, but they are not super attracted to the nucleus. So that tells us that both of these atoms have a low electronegativity, which is reminiscent of a metallic bond. If we wanted to explain why, or exactly what's happening here, we could say that because both atoms have a low electronegativity, and because electrons are super tiny and moving super fast, the electrons will spend most of their time on the outside of our electron cloud. You could also mention that because there's a low electronegativity, there's low attractive forces, so we would expect the electron clouds to be really, really big because there's nothing raining those electrons in because we have that low electronegativity. So that explains all three of these models. In the covalent, the electrons are stuck in the middle. In the ionic, electrons have left one substance or one atom to join another. And then in the metallic, the electrons are on the outside and they're not being pulled in with a lot of force. So that means these electrons can move around a lot. So the last bit that I want to talk about actually has to do with our claim, evidence, and reasoning from the graphing lab. So if you don't have that out as well, pause the video real quick, pull out those results. I'm going to erase everything that I have written here so that we can talk about this in another context. But the important thing to remember is that A is covalent, B is metallic, and C is ionic. So you can pause and come back, or you can just watch me erase as I go through this. Just clean up a little bit. I'll leave our labels because I think those are going to prove to be important. All right, for our claim, evidence, and reasoning that we're working on with this other lab, we need to be able to justify why electrons flow really well in metallic bonds, don't really flow at all in covalent, and float okay in an ionic bond once it's been dissociated. So to do that, we can look at these models and think about what extra electrons are doing. So we started the metallic bond claim together. We said that a metallic bond is made of two atoms that have low electronegativities. And then I asked you to come up with some form of evidence. The best evidence that I would have grabbed would have been the range for the high electronegative atom and the range for the low electronegative atom. And what we should have seen is that both of these were from like 0.5, because remember 0.7 is the lowest one, all the way up to 2. Sorry, I'm writing a little bit small, 2.0. And then the range for our low electronegative atom would have actually been the same, from 0.5 all the way up to 2.0. Somewhere in there. So our atoms have really low electronegativities. That's our evidence. For the reasoning, I wanted you all to talk about how electricity would interact with these electronegativities. So remember, electricity is the movement of electrons. So if I wanted to try to pump electricity through B, that means I would take an extra electron and try to pump it through here. Let's just think about what would happen. If I add an extra electron, my electronegativity is low. These atoms are not attracting that extra electron towards each other. All of the electrons in the electron cloud here are on the outside. They have low attractive forces. So if this electron comes in, it will zip around the outside and it would be able to move on to the next metallic bond. And then it would be able to loop around the outside there, move on to the next metallic bond, loop around the outside, move on, loop around the outside, move on. And this leads to metals being really good conductors. So for your reasoning, you could have said something like, a metallic bond is a good conductor because all of the atoms have low electronegativities, which means that the electrons could flow freely through the substance because nothing is ever going to pull them towards the nucleus or cause them to get stuck. Let's look at A. If we look at A, now we see both atoms have high electronegativities. They're all above 2. If I take an extra electron and tried to pump it through my covalent bond, it might be able to zip around a little bit, but then it would just get stuck in the middle because that's where my attractive forces are really high. So I pump in an electron, it just gets stuck in the middle. I pump in an electron over here, it can roam around, it gets stuck in the middle. Pump an electron on this side, whoosh, gets pulled into the middle because that's where the attractive forces are the highest. So when we're defining our covalent bonds, when we're in our reasoning section, we could mention that covalent bonds are not good at conducting electricity because all of the electrons would get stuck in between these highly electronegative atoms. They wouldn't be able to overcome these electronegative forces, these attractive forces, and the electrons would get stuck inside the substance. In the metallic bond, they're just loosely held on the outside, so they can swing around the outside and then exit. In our covalent bond, they end up getting stuck in the middle. Those are kind of our two extremes. Metallic bonds, really, really good. Covalent bonds, really, really bad at conducting electricity. And then our last one, last claim, evidence, and reasoning we can talk about is the ionic. I think this one is kind of the hardest, but once we walk through it, hopefully it makes sense. Remember, we've got our full positive charge and our full negative charge. What's going to happen here, if I add an electron, where's that electron going to be attracted to? It's negatively charged, so it would come in and it would be attracted to the positive. But then this other atom, let's just say this is sodium chloride, table salt, to make our lives easier. The sodium would be positive, pulls in that electron just as I have drawn. But then chlorine, because it has this high electronegativity, might be able to rip that electron away. And then that frees up another positive, so another electron can come in. There might be another positive atom over on this side. It could then rip the extra electron away to become neutral. And then we might have another chlorine that has a negative charge. That will pull the electron. So as we pump electricity through these ionic solutions, we would see that the electron jumps from positive to negative, positive to negative, positive to negative, all the way until it gets to the other electrode or the other side of our battery or however we have our setup. So if we wanted to break this down into words, we could say something like ionic bonds are pretty good conductors because the positive and negative ions provide a pathway for the electrons to jump through the solution. An electron would be attracted to a positive ion until one of the electronegative atoms plucks it away. And then it would be attracted to the next positive ion until the next negative atom plucks it away. And this process would just keep repeating over and over until it gets to our other electrode. That breaks down what I wanted us to get from these models. But now we're going to transition and put all of this into a notes page. So for the next video, I actually need you all to pull out this page here. Yours looks a little different because there's already some words on it. But in the next video, you're going to watch Mrs. Cat go through these different types of bond character. One of the big things we wanted you to learn from the graphing lab is that there's not necessarily pure ionic bonds, pure covalent bonds, and pure metallic bonds. Instead, we want to start thinking about bonds as a spectrum. So a bond could be more ionic or more covalent, but there are very few instances of what we would call a pure ionic bond or a pure covalent bond. Instead, they're going to be somewhere along this spectrum. So that's what we're going to go through in the next video, but make sure you keep following along. Thanks, everybody. Have a day.